Hey, let's talk about the urinary system. So, a lot of times when people think about the urinary system, they think it's all just about pee or urine. There's actually a lot more going on. So, we see the result of the urinary system as what we urinate. And you may have seen this meme going around the last year or so where, what's my pee telling me? And so there's things like, is your pee very foamy? Is it a weird color? Does it smell a different way? So these are all indicators that something may or may not be wrong with your urinary system, and it's more than just your urinary bladder. So let's go through and talk about it. So the urinary system is actually, it starts in the kidney. It involves the heart and the diaphragm and things like that. These are kind of, well, yeah, we'll get into it. But it's mostly, it involves the kidneys, the ureter, the urinary bladder, and then the urethra. So these are the four big players. So the kidney is going to be what produces the urine. It's basically the filtration system for all of the blood. The ureter is just a transportation. It's just the tube that takes the urine from the kidney to the bladder. And then the bladder just stores it. And then the urethra is just the tube that goes from the bladder and then outside the body. So it's so simple. Oh, but wait, there's more, because of course there is. So what's the function of the urinary system? It doesn't want to let me. Okay, so the function of the urinary system is osmoregulation. This is the balance of water and salt in our body. This involves balancing electrolytes such as potassium, sodium, chlorine, calcium, etc. We've seen these all be really important in the skeletal system or the nervous system and other things like that. Okay, so if you're balancing your salts, you need to be able to balance your water. So our urinary system does this. One of the best indicators of if you are dehydrated is, first of all, if you just feel kind of weird and you don't know why, you're probably dehydrated. So first thing is drink some water. That's not a doctor's opinion. It's just a common thing is that we tend to dehydrate ourselves. Another thing is if your urine is darker than normal, you're dehydrated. So definitely drink more water. The urinary system helps us by regulating water and salt. It helps regulate our blood volume and our blood pressure a little bit, well, a lot. It also regulates this acid-base balance that we discussed in the blood system as being so important when dealing with how hemoglobin works. So in certain acidic or basic environments, you get a better or worse binding of oxygen to hemoglobin. The urinary system is one of the ways that we can get rid of waste. So remember that also includes the secretory system or the skin and the integumentary system, which is the skin, and the digestive system. Okay, so that's important. There's some endocrine functions going on here, such as erythropoietin and renin are two important ones, and we'll talk about those. There's several others too that we'll get into as well. So what is urine at all? So urine is just a way for us to take in good stuff and get rid of bad stuff, which is a very oversimplification of what's going on here. But anytime we have too much water, too many ions, etc., and we have these nitrogenous wastes. So anytime you build or break down a protein, you end up with excess urea or nitrogenous bases. And if you keep those in your body for too long, they can actually start breaking things down in a bad way. And so they cause havoc, basically. They're a waste product. So we want to get rid of excessive ions. And we want to get rid of nitrogenous waste without losing stuff we actually need, like good ions, glucose, which is sugar, which we need to power everything, amino acids, vitamins, minerals, etc. Anything we actually need to keep in our body, we need to be able to absorb back from the bloodstream without losing too much in our urine. So what is going on? Whoop, hello. What's going on? What is this urea you speak of? Why is this bad? So anytime you have an amino acid, which is the building block of a protein, that anytime you hook one of these up to another one, anytime this amino acid is then broken down, you're left with this nitrogen side, this inner carbon, and then this well, basically, anytime two of these come together, you end up with this nitrogen side, this carbon, an extra oxygen, and then another nitrogen side. This is called urea. It's a molecule you don't want to build up in your body because it can start to break things down in a bad way. So it is a definite waste product you need to get rid of, and it's what gives urine its characteristic smell. So that pee smell that you definitely know you're smelling, that is caused by urea. If you have cats, you know cat pee has a very specific smell. They have a different form of urea, a slightly different form that's much more potent. It's very much more powerful to our noses, and that's what you're smelling there. It's basically the same thing. So let's look at the parts of the kidney. So where does that urea come from? How does it end up in our pee? So everything has to go into, all the blood ends up filtering into the kidney. So it comes in through this artery. So remember, artery means away from the heart, which means it's going to the organ. And then it's going to be, the bloodstream is going to be broken off and go into different parts of the kidney, do some stuff, and then whatever we keep comes back through the vein. Anything we get rid of is going to go out through this tube, the ureter. So let's look at these parts. So the functional part of the kidney is called the nephron, and there's a billion, I don't know how many there are. There's many, many, many nephrons. This is just a example of what one might look like here. They're a lot smaller than this. And it's very important that the nephron goes both into the cortex of the kidney and the medulla. So remember, the medulla is the middle, think about the M words there. The cortex is like the outer edge of the kidney. These have very different salt concentrations, which makes it very important for osmoregulation. So that's why that's important, that part of the nephron is in the cortex and part of it dips down into the medulla. We'll talk about that specifically. Okay, so when urine is, why is this being weird? When urine is being produced, whoops, I want this. Da-da-da. There we go. When we are draining urine out of our kidney, we have to first, don't worry about all these extra words, but we do know that, so basically you go through the nephron, and then you're going to be drawn out into the ureter, or the first part that's going to end up draining into the ureter. So we have this collecting tube here, and then it goes into this minor calyx, which is this part here, in which all the minor calyxes or calyces go into the major calyx here. And then they all gather in the renal pelvis, which is this gianter part here, and then that all filters or kind of funnels into the ureter, and then the ureter is going to go to the bladder, and then the bladder to the urethra, which then leaves the body. So let's look and see, okay, so the functional part of the kidney is the nephron. The kidney is basically made up of millions of nephrons. So what is going on with that? What is a nephron? So the nephron is what converts blood into urine. So it's not magic. It doesn't, magically go, oh, now you're urine. What it does is it takes out the stuff that you don't need from your blood. It goes in through so blood's coming in through this capillary bed. Okay, so it's coming in through the renal artery. It splits up into smaller and smaller arterioles, then gets sent into this specific kind of capillary bed called the glomerulus. So that's an important word to know. The glomerulus sits inside the Bowman's capsule. Again, important word to know. And that is where the blood is interfacing with the nephron itself. So when the blood is interfacing with the nephron, everything in the blood, besides cellular products and really big proteins, actually leaves the blood system and goes into the nephron. Okay, so there's less stuff coming out on this side. Okay, okay, so then what happens? We have this proximal convoluted tubule. The blood's going to go through there. Some stuff happens. We'll talk about it. And then some more stuff's going through here. You can see the pressure here would increase because we have a smaller tube. It's like when you put your finger over a hose as it's being used. And so now we've gone from the cortex. As soon as you hit the tube, did I say collecting? This is a collecting tube. This is the loop of Henle. Okay, so as soon as we go from the proximal convoluted tubule into the loop of Henle, we've suddenly gone from the cortex to the medulla, and there's a different osmoregulation environment going on here. There's a different amount of salts in the medulla outside in the environment that are influencing how stuff can move across this membrane than there is in the cortex. Okay, so blood keeps moving, something's happening to it while it does. What's happening? We'll talk about it. And then it's going to enter once it passes again over into the cortex, we're in the distal convoluted tubule. There's some kind of fine tuning of what's allowed to stay in the blood and what isn't. And then basically everything that's left the nephron by this time has gone back into the bloodstream. So there's a capillary bed all around outside the nephron that's absorbing stuff back into the bloodstream. Anything that the body does not want to keep, it keeps inside the nephron. So like the waste products and the broken stuff and anything gross and excess water gets dumped into the collecting tubule, and you can see lots of nephrons connected to the collecting tubule, and starts to concentrate it, and that's where it is technically urine at this point. All right, cool. So again, we have the glomerulus is that capillary bed. The Bowman's capsule is the part of the nephron that encapsulates that glomerulus, that capillary bed. Then we have the proximal convoluted tubule, which we'll talk about. And then we have the loop of Henle, the distal convoluted tubule, and then the collecting duct. So what do they all do? Woo, what's happening here? Da-da-da. Hang on. Go. Oh, nope. Let's not do that. All right, good. That was good lecturing. Okay, so let's remind ourselves of what it means to cross the plasma membrane. This is going to be important because everything that's being taken, anytime something wants to leave the nephron, it's going to have to go across the membrane of the nephron. So if this is the inside of the nephron, this would be the outer cellular, extracellular matrix, the outside. If it wants to leave the nephron, it has to do it one of several ways. So we can either do it through osmosis. Remember, osmosis can only be done by water. And this is always moving from areas where water is more concentrated to areas where water is less concentrated, which means there's more salt. So water always follows the high levels of salt or sugar or whatever the dissolved solute is. So water is a specific kind of diffusion, but diffusion is a generic, well, it's a general term for when very small uncharged particles and some polar, well, I guess we could fit water into this, so basically for small uncharged and non-polar stuff to move across the membrane. So again, it's going to be moving from areas of high concentration to areas of low concentration. So if in this case, so these are all examples of bulk transport, but if these things could cross the membrane and go this way, they would go this way because there's a lot more of these little blue guys and these little stars on the outside. They want to be able to distribute to, so they have an even amount inside and outside. So they want to push in this direction. So if they could diffuse, they just go right across the membrane. There's filtration. So this is just how pressure or gravity pushes stuff. This is again how small molecules cross semi-permeable membranes. So this is like a coffee filter, right? So coffee filters work because they are permeable to water and the molecules that are in the coffee, but not the coffee grounds themselves. And so then you're pulling that water that's then got coffee molecules dissolved in it through the membrane, but the big stuff stays behind. That's going to be a big part of filtration in the kidney. We have transport that requires proteins, which means they also require energy. Okay, so anytime you have facilitated transport, you're moving with your gradient. So phagocytosis could be, it's sort of a form of facilitated transport. Usually this involves just a small protein that acts as a gatekeeper that lets stuff in and out. The idea is anytime you have facilitated diffusion, whatever it is too big, like this guy is too big to just cross the membrane, or maybe it's charged or whatever, and it can't just cross the membrane. So you have to have a helper particle or a helper molecule help it. But it's still going to move in the area, in the direction of where it would go normally. So it's going to move from high to low concentration. Active transport moves against the gradient. And oh, right. I guess the facilitated diffusion doesn't require energy because it's still moving with the gradient. If you're moving against the gradient, this is like when you're trying to pack a whole bunch of cats into a bathtub and they're all moving against you. It takes a lot of energy to keep all those cats in the friggin' bathtub because they don't want to be there. There's a whole lot of other cats in there. What are you doing? And so anytime you're trying to move against a gradient, you have to use a lot of energy. So if we were trying to take this particle and move it outside the membrane where there's already a lot of particles, it would take energy to push it against where it naturally wants to go. Okay, so we also have these two kinds of bulk transport. We have endocytosis, which is where you take something in. So this is endocytosis. So penocytosis is just a form of endocytosis that involves small vesicles. Endocytosis is where you have a bunch of stuff outside, you need to take it inside, so you create a little bubble, and then it comes in through that little vesicle. Phagocytosis is a bigger example where you have something very giant and has to take a very big part of the membrane to like encapsulate the whole thing and bring it in. You usually see this in white blood cells when they're capturing and destroying bacteria. All right, so these are important because we use all these things when we're looking at the nephron. So a very good thing to do in this case, if you are practicing for the test, is to draw these. Okay, so draw that we start with the reference would be this. You start with the glomerulus, and this could be flipped on the other side. So I usually draw it more like this. It doesn't really matter. But you start with the glomerulus and the Bowman's capsule here. You go into the proximal tubule, the loop of Henle, then the distal tubule, and then the collecting duct. So make sure you can draw all of those things and you know the order because it's going to be important when we talk about what they do. Okay, so the glomerulus. What is going on with the glomerulus? So this is a very specific kind of capillary bed. It's extra leaky, and it's surrounded by the Bowman's capsule. And so this is where that idea of get rid of everything that we don't need, but keep the stuff we do need comes in. So the idea is everything in the blood leaves the blood at this capillary bed, at this glomerulus, except for the really big stuff like cells and big proteins. And then at the end, it picks up, basically it's all the rest of that blood, the water component, the plasma component, the sugar component, the vitamins, etc., will be picked up later. But it's a lot better to make sure you clean everything in the blood, even if it's kind of overkill, than to let anything get by. So that's the idea of why all the blood gets filtered in this system. We do about 180 liters per day. That's 25. So basically your blood is getting cleaned 25 times a day. So be kind to your kidneys. So what happens once you go from the glomerulus into the proximal tubule? So there is the blood flow comes in here, and that vein, well, I guess we're still in artery here. Anyway, the blood vessel actually goes with, it's like paired with the nephron, so that anything that's in the blood that the blood still needs, that's actually, okay, so this, for all the kidney knows right now, this is all urine. Everything from the blood except for the cells is right here, which means there's nothing here in the blood system except for the blood cells and the really big proteins. So they're just kind of chunking along, right? It's a very slow process. And then it's right next to now this nephron, where in the proximal tubule, it's very leaky to sodium and potassium and chlorine and phosphate, all the stuff we really want, including water. So we know we got rid of all the water here. All the water is now in the nephron. There's no water in the blood system. Well, the blood system needs water to work, so it's definitely going to allow water to move from the nephron back into the blood system. So that's a very specific filter. The water is going to go back into the blood system in the proximal tubule. At least a lot of it is. So enough that it then balances with the amount of salts or ions that are also moving from the nephron into the blood system. So what happens? So we know that sodium and potassium are reabsorbed by active transport. That we learned about active transport of sodium and potassium back in the neuron unit. So there is a sodium-potassium pump that makes sure that happens. We have these negatively charged ions that are attracted. So the sodium and potassium are here. They move. They're forced to move over here. Okay, cool. Well, now the blood is extra positively charged, which means the negatively charged stuff is like, oh, I'm going to be attracted to that because positives and negatives attract. Well, the sodium and potassium are not allowed to leave the bloodstream, so the negatives move to where those are. So now we have some positive stuff and some negative stuff. So as we get more and more ions here, it's getting more and more salty, we're going to allow more and more water to move from the nephron into the bloodstream. So that's good. We also, in the proximal tubule, have these active transport places where glucose, amino acids, vitamins, and other good things are saved from being urinated. Awesome. So why are these called the convoluted tubules? Because they look really convoluted, because biologists like to say it like it is. So when they were naming these things, they're looking at kidneys up close under microscopes. They're like, this is incredibly convoluted. It's all like, oh, what's even happening here? And so that's what it is. You get this, the blood vessels dump all of that volume off, and then the blood vessel gets wrapped up in the proximal convoluted tubule. The loop is less convoluted, so it didn't get that name, and then it gets convoluted again, but this is the distal convoluted tubule. So the blood vessels that surround the nephron are called the peritubular capillaries. Important, hint, hint. Cool. So what happens in the loop? So in the loop, these numbers are how salty the water is, basically. So how much, what is the percent osmolality, or the osmol, I guess, of the blood itself. So we're losing more and more water to the capillary that's surrounding the loop, which means it's getting saltier and saltier, which means it's going to get harder and harder to pull any water out. Okay, so really the water wants to go the other way, but we don't want it to, because we want to keep the water in the bloodstream. So how do we make sure that that happens? So the descending loop, so if we say the loop, part of the loop that's going down is passively permeable to water, that's really all that's happening. It's just absorbing as much water as possible. And then, well, we still need a whole bunch more sodium and chloride. There's a whole lot of sodium chloride in this ascending loop. And remember, now we're in the medulla, so this is now a very salty environment compared to out here, because you don't want the, you don't want the, well, basically, it's important for the osmoregulation of what's happening here. Okay, so you don't want to be, what am I told? This is great lecturing. You don't want to be losing salt, to the environment just kind of crazy. So you'll notice if this is getting salty, if you want to really be really careful about where the salt is moving, then the outside environment that's not the capillary also has to match this, so you don't just lose water into the kidney randomly. It wants to go directly into the capillary bed that's right next to it. So how do you then maintain that this area is really salty, but then as you go up, it's not like pushing really salty slush through the kidney? Well, here you have active transport of the sodium and chlorine going into the bloodstream to then be recollected by the blood, which again, remember, we need sodium and chloride to do a lot of things in our body, so it's a very important, these are two very important molecules we need to make sure we don't just get rid of. Yeah, good. Okay, so awesome. We went through the glomerulus, which is where the blood system pushes as much as it can into the Bowman's capsule, into the proximal collecting duct, which is where a lot of water is collected and a lot of salts and sugars and things like that. The descending loop is where a lot of water, more water is collected. And remember, now we're in the medulla, okay, not the cortex. The intermedulla is incredibly salty, but we still want to be able to collect salt. And so we have active transport of sodium chloride from the nephron into the blood system. So even though it's not drawn in here, there is a peritubular capillary very, very closely associated with the nephron. Cool, so then what happens in the distal tubule? Basically more of the same. There's some really fine tuning to make sure that we have exactly the right amount of salts that we want to take out of the urine to then put back in the bloodstream. And then we go into the collecting duct. So the multiple nephrons will connect to one collecting duct. Here, the only thing that really moves across the membranes is water. So this is where we can really make sure we're pulling out as much water as we need, especially if we're dehydrated. This is where your urine becomes extra, extra concentrated. Let's see, this is like, yeah, so this is the extra concentrated part of urine production. This is actually interesting. The Nobel Prize recently was awarded to the people who figured out there are these little pores called aquaporins that open or close depending on your hormonal state. And I'm not talking about estrogen, I'm talking about ADH or antidiuretic hormone, which is also called vasopressin. If you are under the influence of alcohol actually turns off vasopressin, which means you no longer can collect water from your collecting tubes, from your collecting duct. So you pee a lot more when you're under the influence of alcohol because you can't retain water at this level of the nephron. You can retain it at other parts, but not this part. If you're drinking, there's another hormone called aldosterone, which is what goes and turns on these active transport proteins, same thing, where if your body says, oh my god, we need to start collecting more water, one way to collect more water is to collect more salt, and then the water will follow. And so if you turn on the salt collecting areas, these active transport pumps, you're going to start collecting water with it, especially here. Aldosterone is what turns that on. If you're, there's some evidence that caffeine actually turns that off. And so if you're under the influence of caffeine, as I usually am, you are not collecting the salt and then you urinate more, but it seems to be a more transient response, so it goes away more quickly. Okay, let's keep going. What else is happening? So what's happening in the distal convoluted tubule? So this is where a lot of sodium reabsorption happens through active transport. We also have, if sodium transport is happening actively, then potassium, this is making the peritubular capillary really positively charged. Then that means other positively charged stuff is just going to go away because it's like, I don't think so. It's going to repel it because two like charges are going to repel each other. So that's going to go away. We can get rid of a lot more potassium than we can sodium. You'll notice that when you're coming in, there's a whole lot more sodium here than we need. And so this is a nice way to balance those ions. So, and again, this is just another place where electrolyte balance and acid-base balance comes into play. Just if you are controlling how many positive ions are going in and out of your bloodstream, you're controlling your acid and base balance. That's as much as you really need to know for this class. And again, the collecting duct and the distal convoluted tubule can be controlled hormonally, like we were just saying. Okay, let's go on. So, what about some more hormones? So this part right here is what I just talked about how aldosterone, and let's make this a little smaller. So aldosterone, an antidiuretic hormone, or ADH, stimulate the increase of retention of salts and water. Okay, what's the word I'm looking for? Respectively. So aldosterone controlled salt, antidiuretic hormone. So a diuretic makes you lose a lot of your water weight, so it makes you lose water. And so if you have an antidiuretic, you're retaining water. Hey, stop! Dog is scratching things. What these do is together they stimulate increased retention of salt and water in the distal convoluted tubule and the collecting duct, which increases your blood volume. So if you have low blood pressure, these tend to go up. If you have high blood pressure, they tend to go down, or you may be given a blocker for these hormones. Okay, so what about this renin-angiotensin system? So this is where the liver, the kidney, and the lungs come into play, which is a very weird thing. Why would the lungs be involved with urine production? Well, it turns out low blood pressure gets sensed by the kidney, and it causes renin to be released. So renin, if you think about renal means kidney, so renin is the hormone from the kidney. That, when it goes into the blood system and then goes back and hits the lungs and the liver, it causes two different hormones to be released. So the liver releases angiotensin 1. When angiotensinogen, sorry, when that then goes through the lungs, you get these angiotensin converting enzymes, which are actually causing the lung to act as an endocrine organ, and it just causes all the suite of things, that I mean suite as in like series of things, that cause you to increase your blood pressure. So it causes all of your blood vessels to decrease. So this hormone coming from the lungs gets sent back. So remember, when blood is coming from the lungs and going back to the heart, that's a good place where you can say, hey, we need to do some vasoconstriction. We need to, when this blood gets to the brain, it'll send a signal saying, hey, adrenal glands, which are right above the kidney, we need you to release more aldosterone so you can retain more salt and water. When it gets to the brain, this angiotensinogen, it causes antidiuretic hormone to be increased, and then it causes, again, more water retention. One of the best ways that our body deals with low blood pressure is it makes you really thirsty, because one way to make sure you retain water is to take in a bunch more water. So if you ever just get randomly thirsty, it could be the result of this you could have a lower blood pressure because you're getting dehydrated, and your lungs are actually involved in telling you that you need to drink more water. All right, so we went through this already. So what do we do next? So we've created our urine. Now what do we do with it? So the urine travels to the bladder through the ureter. So when all the collecting tubes come together, you get the ureter. So that's the connecting tube between the kidney and the bladder. Remember, the kidney's kind of weird because it doesn't sit in the cavity, the visceral cavity with all the rest of the organs. It kind of sits right outside. So if you've ever heard of a kidney punch, it's someone hitting the back and actually literally hitting the kidney. It's not really protected very well. Whatever. Thanks, evolution. The bladder has all these folds inside of it that allows it to stretch. So the urinary bladder, the only thing the bladder does is it stores urine. It doesn't do anything else. It's not possible for you to hold so much urine for so long that your bladder explodes. It's just not possible. What will happen is your urine eventually, there are sphincters in the urine to make sure you have to learn when to and when not to release your urine. Like as a kid, you learn when it is and it is not appropriate to pee. So that's potty training. When you're very drunk or as you get older, the part of your brain that tells you what is and is not appropriate starts to go away. Those inhibitions start to go away. So it's not that your bladder gets weaker, it's that the control system in your brain that's saying, don't pee now, starts to go away. Okay, especially if you're drunk, that inhibition that tells you, don't pee right now, it's not appropriate, goes away, and then you have to pee so many more times. You think you have to pee a lot. And that, on top of having no water retention in the kidney, makes you pee quite a big amount. Okay, so what else? There are a lot of sphincters, both inside the bladder and in the the urethra, sorry, that comes out of the bladder. So this is the prostate. It's involved in reproduction, not urinary system, and it's not present in females. But the sphincters in the bladder and outside the bladder are the ones that keep you from peeing yourself when you don't want to. So how do we get urine to move through the ureters? It doesn't just like open up a tube and it just like flows through. There's actually a wave of muscular actions like in the colon or in the esophagus that moves it all down through peristalsis. What else do I want to say about this? I think that's good. Okay, so let's talk about acid base. Really, that's all you really need to. So the interesting fact about the urethra is that it's a lot longer in males because the urethra in males functions as both a urinary. It has both urinary and reproductive functions, so you have this added length through the penis. In females, it ends right here, and then we have, or actually, I guess it goes down more, and then it is not the same as the hole used for reproduction. That's a very common mistake. People think it's all one thing. It's not. It's different. And then, so a lot of times when you like have this like, oh no, I have to pee right now, what's happening is one of the sphincters releases a tiny bit of urine to like the next set of sphincters, and it's kind of like a little tapping on the door, like, hey, we got a full bladder, let's make this happen. And then that tells your brain, can we do this now? And then your brain, you get to then consciously decide, can I urinate right now, or do I need to go find a bathroom or whatever? So it's actually a very strangely complicated process, the process of urination. Oh, we don't care about that. Let's talk about this. Okay. Back to acid-base balance. So our kidneys help control the acid levels in our body. Remember, this is also controlled by carbonic acid and bicarbonate. So when we have all this extra, so when we talked about blood, we talked about how we can store a lot of that carbon dioxide instead of in hemoglobin, we can store it in the blood as carbonic acid or as a bicarbonate ion. These travel through the blood nice and easily, but we didn't talk about where a lot of those hydrogen ions come from. So if you have just a whole bunch of hydrogen ions floating around, it becomes very acidic, and that's very dangerous. Okay, so when you have water in the presence of carbon dioxide, they'll react and you get carbonic acid. When they continue to react, a more stable form is the bicarbonate ion, and then the hydrogen ion. But if you have just a bunch of free hydrogen ions floating around, they can go and disrupt things, which means you have to be able to get rid of hydrogen very easily, and that's where the distal collecting tubules or distal convoluted tubule comes in, which is really important. It's also another important function of carbon dioxide to allow, well, maybe you don't have enough hydrogen, so we actually need to break down more of this carbonic acid to allow more hydrogen to be present. It's a nice push and pull system. Okay, so let's talk about this. So it's interesting to think about if you breathe too fast through anxiety, you don't collect enough carbon dioxide, and so your blood becomes less alkaline, becomes less acidic, so it's more alkaline. If you drink too much sodium bicarbonate, or like if you eat too many Tums, you also get really alkaline blood. Your blood acidity goes down, and you may be asking, well, is this good or bad? If I lose a bunch of stomach acid, I get really alkaline. Is that bad? Well, it's all about balance, okay? Because you don't want to be too acidic, but you don't want to be too basic either. So it's all about balance. All of these things are not something you want to be just in a constant state of. You don't want to constantly be anxious and breathing too fast. You don't want to be constantly at a high altitude with low carbon dioxide. Your hemoglobin will actually increase in numbers in your blood system to make sure you collect enough oxygen from the air and then have enough carbon dioxide in your blood system to help with those acid-base problems. That is very important, so that becomes important. If you have something like emphysema or pneumonia, in both of these cases, you don't have enough alveoli in your lungs to pull in enough oxygen. If you don't have enough oxygen and you don't have enough places to get rid of carbon dioxide, you end up with a whole lot of carbon dioxide. You have very acidic blood. Let's take a second and go back and talk a little bit about some renal, let's talk about this. So let's talk a little bit more about, I don't know why my slides are showing that these aren't. Anyway, whatever. Let's go back to the bladder a little bit. What else does the bladder do? So the bladder does not allow anything, really nothing really happens in the bladder. It just stores the urine. It can store about 300 milliliters of urine each at the most. Once it hits that, it will stimulate these stretch receptors, which then tells your brain, I have to pee. Then, like we said, then that internal sphincter is going to relax and it sends a bit of urine to your next sphincter, and then it tells your brain, oh my god, I really have to pee. And if it's okay, you pee, but if not, you don't. And so in the case of infants or people who are highly intoxicated, or if you're freaking out, if you have really high stress levels, like in the case of a fight or flight system, you can't control that external sphincter because your brain can no longer do it, and you will urinate. So what happens in the urethra? Urethra is just a tube that will allow the urine to travel from the bladder outside of the body. That's it. And like we said, it's much shorter in females because we just go from bladder to, I think in this picture it makes it seem like it's really far away, but it's not. This is over exaggeration. It's much closer to the external side than it seems. In the male, because it acts as both a reproductive tract and a urine tract, it is much longer. There are so many things that can go wrong in the urinary system. Usually it's because of the flow of urine being disrupted. You can have cystitis that's often caused by bacteria or fungus or viruses getting into your body through the urinary system. Because like we usually say, anytime you have an orifice from the internal side of your body going outside the body, you have mucus. But there's not a lot of mucus in this system because you want to it's just trying to get rid of stuff all the time. Okay, and mucus tends to protect us from bacteria, but the urinary system doesn't have a lot of mucus layers. So cystitis is just inflammation of the bladder. This is much more common in females because we have such a shorter urethra, and so it allows you, it means that there's a better chance for bacteria getting into the bladder and getting a bladder infection or a urinary tract infection because it's so much closer to the outside. This used to misogynistically be called the honeymooner syndrome because suddenly girls were having a lot of sex on their honeymoon, which means there's a lot more presence of bacteria being stimulated in that region and blah, blah, blah. The idea being if you have sex and you don't clean very often, you could very easily get a urinary tract infection. It's actually really good if you're female too, and probably males too, after you have sex to urinate because then you're pushing stuff out of your body instead of allowing it to sit there and grow more. So even though it's not the same hole, if it's sitting kind of outside the same hole, it's like it can get up into the urinary system. The science keeps going back and forth on whether or not cranberry juice really works for a urinary tract infection, but if nothing else, it hydrates you more, which means you're going to urinate more, which means you're going to be more likely to get rid of that bacteria, and also antibiotics. It's very easy antibiotic treatment. You could get an inflammation of the nephron itself. That's called pyelonephritis. You could get glomerulonephritis, which is just an inflammation of the glomerulus. This just means that this is a serious infection that's gone from the external environment up the urethra, through the bladder, through the ureter, and into the kidneys, or maybe even the other way, through the blood system into the kidneys, and you just have to take more antibiotics. It's a much more serious infection, though. Most common is the kidney stone or the renal calculi. It's a concentration of urine. Usually there's a whole lot of calcium going on here and urea that's building up in a way that, like this is an x-ray, these are the kidneys. You can see the kidneys are almost completely filled with a kidney stone. Holy cow, these can be incredibly painful because you're pushing them through a tube that is very, very, very small and is only used to carrying fluids, and it's ringed with muscles that are very sensitive to whatever's happening. And so people have likened the passing of a kidney stone, this one is giant, to things like losing a limb or childbirth or other horrible, painful things. Not that childbirth is horrible, but it's very painful. So if you want to dissolve a very, very big kidney stone, you go through and you look at it through an ultrasound or an x-ray like this, and you ultrasound is not what you used to look at. Ultrasound is a wave of sonic vibrations which go in and try and vibrate it. If it's just not possible, like for some reason it's composed of something that's not responding to ultrasound, you can have surgery. A lot of times you just have to pass it, which means you just have to pee it out, which is a painful process. One of the biggest problems is renal. One of the very common problem in the kidney, not common, but a common pathology in kidneys is renal failure. So if the kidney just straight up fails, a person will die in 1 to 2 weeks from this acid-base problem and your electrolyte imbalance. So the kidneys are not filtering your blood. It's just going to start filling up with stuff that should not be there. But it can be treated. You basically get yourself an external kidney. So you get you go on dialysis. So you get a dialysis machine that takes the blood out of your body, does basically everything that we know the kidney can do, and then puts it back in. We don't. Yeah, it's a very painful process. I think I've been told it's very painful. It's very uncomfortable. We don't have it down to a super great science yet, and it's something where you have to spend time sitting by a machine letting it do this, but it will save your life if you are in renal failure. So it's a very important thing for people who are having kidney problems. I think that's where we're going to end it here, and I will talk to you guys next time. Bye.